Welcome to the tutorial on graphing lines, a skill with application in many math courses. First, some background. A relation is a set of ordered pairs, a list of things in pairs where the order is significant. The members of the list can be anything: numbers, letters, even characters in movies. If the members are numbers, then we have some tools we can use. Specifically, we can draw a graph of the relation. We interpret the first number as the distance along a horizontal axis, and the second number as the distance along a vertical axis. Most commonly, we call these axes the x-axis and y-axis respectively. The relation is then considered a collection of x-y pairs, or coordinates. We make a mark at the points corresponding to these pairs. The collection of points is the graph. Here's a quick example. Plot this relation. As you move forward in math, you'll encounter lots of graphs, many of them more complicated. You can graph any shape from geometry. You can graph any number of points. You can specify the graphs by explicitly listing the pairs as above, or you can specify them through some other way, say through an equation. This is the thing to keep in mind. All graphs are sets of ordered pairs. To be on the graph, the pair given by the coordinates must be in the relation. This is especially important and subtle for equations. Any point on the graph automatically satisfies the equation. That is, it makes the equation true. Consider this relation. That graph is very familiar. These points all seem to fall on a line, and they do. Consider this graph. This line is made of all points whose vertical coordinate happens to be exactly twice the horizontal coordinate. If we represent any point on the line with the coordinate pair x, y, we could connect x to y. That is, y is 2 times x. This would be the equation of the line shown. Notice that this is still just a relation, just like before. It's just that we have many, many more points, in fact an infinite number of them, so we can't list them. But the equation captures all of them all at once. Just like in geometry, one of the most fundamental shapes for graphs is the line. A line has the special property that, if we change the x value by a certain amount, the y value changes by a proportionate amount. And the proportion is the same no matter what the original value of x was. We call that proportion the slope of the line, and we write it as m. Here, m equals delta y over delta x. That triangle symbol, pronounced delta, is the Greek equivalent to the capital letter D. As a side note, apparently no one actually knows why m is used for the slope. Given the graph of a line, finding the slope is easy. Pick any 2 points and use this formula. For example, let's find the slope of this line. Pick 2 points on the line, say 2, 5 and 4, 6. Then the slope, m, is 6 minus 5 divided by 4 minus 2, which comes out to be a half. Notice that we can interpret this as move 1 block up for every 2 blocks over that you move. If instead you move down 1 block, the slope would be negative. But by convention, we always move left to right. What if we had picked different points? Let's try minus 2, 3 and 4, 6. M is then 6 minus 3 over 4 minus minus 2, which is 3 over 6, or a half. It doesn't matter which points we pick. That's actually the definition of a line in coordinate geometry. Although all points on a line are equivalent and you can choose any of them, there are 2 points that get special names and that are useful for graphing. The y-intercept is the point where the line crosses the y-axis. Thus, all y-intercepts have an x value of 0. For the line drawn, the y-coordinates of the y-intercept is 4. The x-intercept is the point where the line crosses the x-axis, and thus all x-intercepts have a y value of 0. For the line drawn, the x-coordinate of the x-intercept is minus 8. Notice that a given intercept is where the other variable is 0. It's a little strange, but true. Often we are instructed to use the equation of a line to construct its graph. Luckily, it's fairly straightforward. Actually, there are many equations for any given line. We generally focus on 3 particular forms: point-slope form, slope-intercept form, and standard form. Point-slope form. The equation of a line with slope m passing through a given point h, k is y minus k equals m times x minus h. Often the point to use is clear from the problem, especially when that includes the line through a particular point. For example, the line passing through the point 4, 1 with a slope of 2 would have the equation y minus 1 equals 2 times x minus 4. If you're given an equation in point-slope form, it's easy to graph. Start at the given point, then move rightward by delta x and upward by delta y. Or, of course, move downward if delta y is less than 0. That's your second point. Then draw the line connecting them. As an example, graph the line given by this equation. Y minus 4 equals 2 times x plus 3. The first thing to notice is it's not quite in the right form because we need x minus h, but we have x plus 3. But actually that's fine. We just use the fact that the role of x minus h is being played by x plus 3, so we set up that equation and solve to find that h equals minus 3. Thus, the given point is minus 3, 4, and the slope is 2. We start at minus 3, 4. The slope is 2, which of course is the same as 2 over 1. So delta y is 2 and delta x is 1. That means we go rightward 1 unit and upward 2 units to reach minus 2, 6. That's our second point. Now we run our line through those 2 points. Slope-intercept form. A different form of the equation of a line is slope-intercept, where we're given the slope, of course, and the y-intercept. It's always the y-intercept. If you're given the equation and you need to make the graph, it's still pretty easy. Find the y-intercept using b and start there. Then use the slope to move to another point. Finally, connect those 2 points with a line. For example, graph the equation y equals 3x minus 5. The y-intercept is 0, minus 5, since b equals minus 5. Notice that's what we get if we plug x equal to 0 into the equation, since that's how we generate y-intercepts. The slope is 3. So we start at 0, minus 5, and we move over 1 unit and up 3 units to 1, minus 2. That's our second point, so now we can just connect up those points. Standard form. Ironically, there are actually several variants of so-called standard form, but they all cast the line into an equation looking like ax plus by equals c. To go from an equation in standard form to a graph, use the equation to find the intercepts, then connect them with a line. As an example, graph the line given by 6x minus 4y equals 18. First, we find the x-intercept by setting y to 0, or 6x minus 4 times 0 equals 18, giving us 6x equals 18, or x equals 3. This means the x-intercept is 3, 0. Then we find the y-intercept by setting x to 0. So 6 times 0 minus 4y equals 18, minus 4y equals 18, or y equals minus 4.5. So the y-intercept is 0, minus 4.5. Now we just graph the x-intercept and the y-intercept, and then connect them with a line. On a horizontal line, all the points share the same y value, but can have any x value without restriction. This is given by the equation y equals k. For example, graph the line y equals 2. We pick some points that we know are on the line. Any 2 will do, but we know that each must have a y value of 2. Let's try, say, 0, 2 and 1, 2. Then we connect them and voila, a horizontal line results. Likewise, on a vertical line, all the points share the same x value. We can have any y value without restriction. This is given by the equation x equals h. For example, graph the line x equals 3. We find 2 points that satisfy that equation, which can be any 2 points as long as they each have an x value of 3. So let's use 3, 0 and 3, 1. Connecting them, we have, as expected, a vertical line. Drawing these 2 together, we get this graph. Notice that the axes are themselves just x equals 0 for the vertical axis and y equals 0 for the horizontal axis. And those are all the different types of equations of lines that you'd have to graph.